Good morning. In last class we have seen what is Hall effect and one of the applications of Hall effect. In today's class we will derive how much is this Hall voltage, what is the magnitude of this, and we will come up with some more applications of Hall effect. According to Hall effect, when a current carrying conductor, when it is placed in a perpendicular magnetic field, a force is acting on these charge carriers, and this force is pushing these charge carriers down. So there is some downward force because of this magnetic field. What is the result of this? A electric field was existed. Now what this electric field will do is, this electric field will pull the electrons up. Now you are having one force, magnetic force, which is pushing the electrons down. Now you are having one more force which is pulling the electrons up. Now under equilibrium, the force because of this magnetic field will be equal to force because of your electric field, and it will stop any further flow of electrons in downward direction. Now let's derive how much is this Hall voltage. Now we have seen that the force because of electric field is equal to force because of magnetic field. I am keeping a negative sign just to represent that these two forces are in opposite directions. Now force because of electric field we can write as Q into E, same minus sign, is equal to Q into B into Vd, where Vd is the drift velocity of these charge carriers. What is Vd? Drift velocity of charge carriers. Now we know we can write E, electric field, as voltage by distance. Now this electric field is equal to voltage, which is nothing but Hall voltage, VH, by distance is nothing but the distance, the height of this semiconductor. This is D. The height of your semiconductor is nothing but D. If you consider this as to be semiconductor, this is the thickness, the height of your semiconductor, VH by D. Now let's write Vd in terms of I. We know the current can be written as area into NQ Vd. From this we can write Vd is equal to I by ANQ, where A is the area of your semiconductor, cross-sectional area. So what is A? If we see the three-dimensional picture of the semiconductor, this we are representing as thickness or height of your semiconductor D, and this as W. Now area is nothing but W into D is the cross-sectional area. The area is nothing but this D into W. The area seen in this direction. Now area can be written as I by A, area W into D, NQ. Let us say this is expression 1, expression 2 and expression 3. Just substitute. By substituting minus Q in place of E, we are writing VH by D is equal to QB I by W D N Q. And after some cancellations, VH we can write as minus BI by WNQ. So this is one of the nice expression, one of the important expression that we can remember. How much Hall voltage is generated? The Hall voltage is generated is proportional to the magnetic field as well as current, and inversely proportional to NQ, means charge density, and width of your semiconductor. This is the expression for Hall voltage. Now, 1 by charge density we can consider as Hall coefficient. 1 by charge density we are calling it as Hall coefficient. In that case, this VH, Hall voltage generated, can be written as Hall coefficient into BI by W. Now, okay, here we can see that for electrons as a charge carrier, this Q, this charge is negative. So negative into negative, VH will be positive. So for a N-type semiconductor, the Hall voltage is positive, whereas for a P-type semiconductor, the Hall voltage is negative. Now let us see some of the applications of Hall effect depending on these expressions, which depends on these expressions. One of the application of Hall effect is, as we have seen in our last class, for a N-type semiconductor, this charge is negative. So negative into negative, positive, you will get a positive voltage, whereas for a P-type semiconductor, you will get a negative voltage. So depending on the sign of the voltage, whether your voltage is positive or negative, you can decide whether a given semiconductor is N-type or P-type. So what is the first application? You can tell that whether a given semiconductor is P-type or N-type. What is the next application? From this expression, you can also find out the charge concentration, the carrier concentration. How can we? We can write that N is equal to minus BI by WQ into VH. So we can conduct a Hall experiment and we can find out how much is this Hall voltage. And depending on this Hall voltage, how much is the magnitude of Hall voltage, we can find out the carrier concentration. We can find out how many charge carriers present, or we can find out the doping concentration. So what is the second application? Depending on the sign, positive or negative, you can tell P-type or N-type. Sign of your Hall voltage. And how much is that Hall voltage? What is the magnitude of this Hall voltage, whether 1 volt or 2 volt? You can tell how many charge carriers present, what is the doping concentration. This is the second application. The third application is, you can also find out the magnetic field present in this room. How can you find out? From this expression only, I can write B is equal to VH WNQ by I. So how can you find magnetic field? If a known semiconductor is given to you and you know everything about the semiconductor, the dimensions, the carrier concentration, N, doping concentration, everything. Now if you apply Hall effect to the semiconductor, if you conduct a Hall test on the semiconductor, the magnetic field, the Hall voltage developed will be proportional to magnetic field. So depending on how much Hall voltage is generated, you can find out what is the magnetic field present in this room. What are the other applications that you can have is, you can also find out the mobility of these charge carriers. not only the concentration, how many charge carriers are present, you can also find out the mobility of these charge carriers. Okay, how can you do that? Here in this expression, RH is written as 1 by charge density. We know conductivity can be written as N Q Ne, otherwise Q, into mu. Now mobility can be written as conductivity by Ne. 1 by NQ, we can call it as what? Hall coefficient, RH. So mobility we can find out by conductivity into Hall coefficient. You can also find out mobility. How can? Just perform a Hall effect experiment on this semiconductor. Find out how much voltage you are getting, and depending using this expression, you can find out Hall coefficient, which is proportional to the Hall voltage generated, and simply mobility is nothing but conductivity into Hall coefficient.